Okay, let's cut straight to the chase on this one. We'll give another example step by step, and then I'm going to turn over the third question to you. All right, so we did one question on Monday. I'll do a second question right here, step by step, and then I'll have you take over with the last one. All right. Now, of course, I've got to have my sides labeled. And of course, if I look inside the integral and say, hey, I'm looking at the leg of a right triangle, right? Because if a squared plus b squared equals c squared, if I solve for one leg, I say, aha, one of the legs is the square root of c squared minus b squared, and that's what I see in my integral. So 9 has to be c squared. So c is 3, that's the hypotenuse. X squared is b squared. So b is x, so that's one leg. And again, I'm going to choose to put it as the opposite side. So later on when we integrate, I don't have to worry about the extra negative involved. And then, of course, I already knew what my other leg was. The other leg has to be the square root of 9 minus x squared. So, of course, I want to be able to substitute something in there for x. And so I'm thinking, well, adjacent side looks pretty convoluted. So let's just go for opposite hypotenuse. We have to use sine. Right? Sine of theta is x over 3. Multiply both sides by 3, and x has to be 3 times the sine of theta. That's my substitution. Need a little bit more room. Now I'm only looking at the square root and what's inside the square root, right? I'm not looking at the entire integral yet. So inside there, the x can be replaced with 3 times the sine of theta. When I square that, 3 times 3 is 9. Sine of theta times sine of theta is sine squared theta. I can use the distributive property, right? There are 2 terms inside that square root. They both have a factor of 9. Right? 9 times 1 makes the 9. 9 times sine squared theta makes 9 sine squared theta. And of course, the identity we use most often in trigonometry, sine squared theta plus cosine squared theta equals 1. That gives me my substitution. The number 1 can be substituted with sine squared theta plus cosine squared theta. Combine like terms, and I've got 9 cosine squared theta. Taking the square root, and I get 3 cosine of theta. Now that takes care of the square root symbol and everything inside the square root symbol. I still have the dx. So let's go over to the right hand side of the screen. Take the derivative of x with respect to theta. Multiply both sides by d theta. I can say, aha, dx can be substituted for 3 cosine theta d theta. That's my dx. Now, we really need to start speeding some of these things up. If you know 2 plus 3 is 5, you should instantly recognize that 5 take away 3 is 2. Same thing with trigonometry. If you know sine squared theta plus cosine squared theta equals 1, you should instantly recognize that 1 minus sine squared theta has to equal cosine squared theta. I might have to put together some flashcards, because obviously this is not all getting brought to memory for all of us. Okay, so let's do our substitutions. I've got a 3 cosine of theta. I've got a 3 cosine theta d theta, right? Those are the two things that we substituted in. Simplifying, 3 times 3 is 9. Cosine theta times cosine theta is cosine squared theta. Now, for upwards of a year, I've been telling my wonderful students that they need to, at the minimum, familiarize themselves with their trigonometry reference sheet, if not flat out memorize the reference sheet, right? Nothing I refer to on this sheet should be that foreign or that strange, right? I've been begging, pleading, advising, recommending that you familiarize yourself with this sheet, if not downright memorize this sheet. Right, so for double angle formulas, there's a couple places where I can identify cosine squared theta, but I do not have the sine squared theta, so I don't want to pick the option that has both cosine squared and sine squared. Instead, this is the option I want. Cosine of 2 theta equals 2 times cosine squared theta minus 1. Right, so that's the one I'm going to play with, because I want to be able to trade that cosine squared theta away for something I can actually integrate. So we add 1 to each side, divide each side by 2, also known as multiply by 1/2. There is my substitution. 9 times 1/2, of course, is 9 over 2. Now I can actually integrate, right? If I integrate 1 with respect to theta, it becomes theta. If I integrate cosine, it of course becomes sine. But are we going to just see sine of 2 theta? No, there's going to be a 1/2 on there. Because of the 2 on the theta, if I do a u substitution, I'm going to have that 1/2 show up. Right? This is identical to what happened with the example on Monday. Right? When we integrated cosine of 2 theta, we ended up with 1/2 sine of 2 theta. Notice at this point the only difference between this example and Monday's example is that we've got a 9 over 2 instead of 25 over 2. That's the only difference. Of course, I need to do my back substitution. The original was in terms of x, and right now I'm in terms of 2 theta for at least part of this, and I need it back in terms of theta because my triangle was in terms of theta. So there's my substitution. And of course 1/2 times 2 will cancel out. So we did a trig substitution so that we could integrate. We then did the integration. Now we just have to do the back substitution. Of course, we already knew that sine of theta was x over 3. That's kind of where we started. So we've got sine of theta taken care of. Cosine, that's simple. Cosine is adjacent over hypotenuse. So the cosine of theta has to be square root of 9 minus x squared over 3. So that takes care of cosine theta. Now, for plain old theta, think about how inverse functions work. For example, if I knew the square root of alpha was beta, I'd know that alpha was equal to beta squared, right? Square and square root are inverses, right? So like if you want to see an example with just plain old numbers, right? There it is with plain old numbers. What if instead I have an exponential situation, such as delta raised to the omega power equals kappa? Well, what's the inverse function? Logarithms. Right? Log base delta of kappa would be omega. Again, if you want to see examples with plain old numbers, that's what it looks like with plain old numbers. So I've got the sine function going on here, right? What happens if I've got sine of tau equals mu? Well, inverse would be arcsine of mu equals tau. Again, with plain old numbers, we've been doing this with a unit circle. If you know the angle is pi over 3, the sine of that angle would give you the ratio of √3/2. That'd be the y-coordinate of that point on the unit circle. Instead, if I gave you the y-coordinate on that unit circle and you wanted to know the angle, you would do the inverse function. You do the arcsine of √3/2 equals pi/3. Right? We use the sine button on our calculators, and then when we use the second function, instead of arcsine, it looks like sine raised to the -1, but that's the arcsine function. So theta has to be the arcsine of x/3. Right? Angle theta corresponds with the arc that is created by the coordinate x/3 for the vertical component. That gets me the theta. So I can do my substitution for theta, my substitution for sine theta, my substitution for cosine theta. We can do a little bit of simplifying. I can use a distributive property, and I can do my final simplification. You'll notice that this answer is extremely similar to what we had on Monday's example, but instead of 25/2, we have 9/2. So this becomes quite predictable. Oh, and also inside that square root symbol, instead of 25 minus x squared, today we have 9 minus x squared. But if you look at the original question on Monday and the answer on Monday, look at the original question today and the answer today, take a peek. There's a lot of similarities, right? And of course, we would have had what, arcsine of x/5 on Monday instead of arcsine of x/3. But the big difference is we started with a 9 instead of a 25, and so instead of 25 and 5 showing up in the answer, we've got 9 and 3 showing up in the answer. So today's assignment, I'm going to start a brand new question, and then I'm going to hand it off to you. But there is going to be a little bit of a twist, okay? There is our friendly integral. You know I'm going to draw a right triangle and label one of the angles with theta. One of the acute angles has to be theta, right? Not the right angle. And of course, if I look inside the integral, I'm thinking, hey, I see the leg of a right triangle, because if I solve for one of the legs from the Pythagorean theorem, I find out that the leg is the square root of the hypotenuse squared, subtract the other leg squared. So that means that my 4, also known as 2 squared, is my b squared. So 2 is b. Now, for this question, I'm putting it in the adjacent side. That's a little bit of a twist. You're like, hey, you didn't do that before. No, I didn't do that before. Remember, before, we ended up putting either a plain old 5 or a plain old 3 for the hypotenuse. Notice that 2 is not the hypotenuse. The hypotenuse is actually x. Right? There's the big twist. Look where the x is. The x is the hypotenuse. And of course, we already knew what the other side had to be. Now, why did I put the 2 on the adjacent side? Because at first glance, you're thinking, hey, this forces me to use cosine. Right? If I've got adjacent hypotenuse as the friendly looking sides, we're doing cosine. Well, again, I know what's going to happen a few steps down the road, and I know when we do integration, half of the 6 trig functions are very friendly for derivatives in integration, and half of the 6 trig functions are not very cooperative because we have to deal with a crazy negative symbol. I don't want to deal with the crazy negative symbol, so I'm setting up the triangle this way. Uh-oh, look where that x is. This is not going to work out very well, is it? I want x in the numerator. Instead of adjacent over hypotenuse, I really want hypotenuse over adjacent. There I have it. Hypotenuse over adjacent, secant of theta. Right? Using secant of theta is going to work out very well with the integration we're going to have to do. So I solve for x. Now I know exactly what has to be substituted for x. So this is not identical to the example from Monday. It's not identical to the example from today, but it is quite similar, right? I start by drawing a right triangle. I label all the sides, and I have done that for you with explanation. And I have identified what needs to be substituted for the variable x. Now, you can use the example from Monday and the example from earlier today, kind of like templates, kind of, advisories on which way to go. It's certainly not identical, but you know what to plug in for x. You'll know that you'll probably have to do some simplification. There will probably be a trig substitution you have to do. Eventually you should get to the point where you have something that you can easily integrate. But then after you integrate, you're going to have to figure out how to do your back substitution, so your answer is going to be in terms of x. Now, is your answer going to include arc sine? Well, we're not starting with sine, so you're going to probably find some surprises down the road. Also, that sine squared plus cosine squared equals 1. That might not come into play because I don't see us playing with sine of theta here. But it's similar enough, and you've got your trig reference, right? I always refer to it as a cheat sheet, but it's really just a nice big reference guide. Call it a cheat sheet because quite often if you're taking like an AP calculus class, you must have all that stuff memorized, right? It would be considered cheating to look it up. But we're not doing a strict AP calculus class, and so you are allowed to use the reference guide. You're not forced to memorize that stuff, but it would certainly be helpful if you did. So it's your turn. You got the triangle. You know the substitution for x. See how far you can get. And now the happy ending. I have noticed in travels, whether we're talking about, the valley of the Yellowstone River approaching Yellowstone National Park, or some of the roads heading up toward Glacier National Park, or the roads heading up to Pinnacles National Monument in California, you get some beautiful scenery, and there always seems to be a cow just hanging out, if not a bunch of cows. Cows seem to have the best patches of grass there is on the planet.